Good evening, one and all. Hadoop is a very big world. It's like in today's era, in big data world, it's a ocean. And what we are trying to cover out here in this session is to just a few drops of water in that ocean. Identically, I would like to cover very high level overview of some of the important components of Hadoop. So first we will understand what the Hadoop is. Second, if we understand what the Hadoop is, then we will understand what all the each component are in the Hadoop ecosystem and how what is their role. So first of all, we will see later how the Hadoop came into existence. But just to give you a perspective, it's an open source system. Dave Cutting was the name of the person who actually laid the foundation of Hadoop, and his idea was based upon the three research paper that Google has produced in 2003, and he invented Hadoop in 2006, roughly, and based upon those three papers were the proprietary of Google, but they made it public. So from there on, it becomes an open source system. Time and time, people came on, added the different component of the system, and enhanced the different component of the system. So what is Hadoop? Open source, we understand. It's an open source software platform. Before we jump onto that, let's take a look at the some of the Hadoop ecosystem. What are the components of Hadoop? So HDFS, YARN. So these are the different sub-component or component of the Hadoop system. Now coming back to the definition of Hadoop, it's an open source software platform for distributed storage, distributed processing of a very large data set on computed clusters. Hadoop is not just for batch processing. So what does it mean? Let me explain you. Distributed. Distributed means it spans across multiple instance or multiple things. That's what at a very high level distributed means. So storage. Distributed storage means the storage is not on just one computer or machine, or you can call it as server. We call it in the definition as node. So it's not just on traditional system. How it used to happen is everything gets loaded onto a cluster of machines, two or three machines, but everything gets loaded over here. In this definition, distributed means it's not just on one server, it's across multiple servers, and people have cluster of servers which is running not in hundreds, in thousands. So some company has got 4,500 servers in the cluster. So that's what the distributed means. Storage, obviously, when you have a data, you need a storage, and when you have to have a storage, it needs to be distributed because it cannot be loaded onto single computer. That's what it means, the distributed storage. Second thing is distributed processing. So obviously, when the data are span across, let's say, 400 servers, one particular server cannot be in a position to process the data across all the 400 servers. So what happens is the processing also becomes distributed. So people think is why just data, why not processing also needs to be distributed of very large data set, which is self-explanatory, on computed clusters. All the computers in the clusters are called node, and all the nodes are capable of storing the data and processing the data. That's the definition of Hadoop. Hadoop, where does it stand in a bigger picture? So on the left hand side, you can see all the source systems. So different businesses have got different source systems, social media, ERP, HR, production, product, and there are a hell lot of source systems, right, which produce the structure as well as non-structured data. The structured data means you can give a structure to the data that you are producing in the form of tables. Unstructured data which cannot be given a shape of it, like video file, images, and things like that. So if you will see on my left hand side, these are the source system, right? So you acquire the data from these source system, then you stage it somewhere before you transform and load, and then you again finally load it into Hadoop. Now, later on, we will see that after loading into the Hadoop, there are data processing also happens with. But for now, you assume that this is the endpoint. And from there, the data has been exposed either through, there are only two channels, either through OLAP, which is the traditional data warehousing, and which one way is via Hadoop or via any big data system. The big data system exposes the data to the end user in a certain way so that the data can be consumed specified to its own use cases. So for an example, customer churn prediction. Whether a telecom company generally pulls the data of the customer calls, their call time, and there are n number of external factors, and they do the analysis and predict that whether this particular customer will churn or not. If it will churn, then how long it is going to take, whether it will churn it in 2 months, 3 months, 6 months, and so on and so forth. That kind of analytics also is possible in Hadoop. So this is just a big picture, nothing related to Hadoop as such, but just to give you a idea where does Hadoop stands for. So here is the Hadoop based big data system. So on the left hand side, you see the data source or the input. And on the right hand side, you see the consumption of the data. Ultimately, data has to solve the purpose of different reports, web analytics, and so on and so forth. And this is what the Hadoop stack lies in the middle. Traditionally, people do, and there are two types of companies also. One is who invest low, and second who invest in proprietary tools also alongside with Hadoop. The first company does everything in Hadoop. So he pulls in the data lake, the data resides in HDFS, it's a distributed file system. They don't touch HDFS data, but they take up the HDFS data, wrangle it using Spark, and then you dump it in another file format, table format in Hive, or and so and so forth. Second set of users takes the data in the HDFS, wrangle it outside Hadoop, and then dumps the final output in the inside Hadoop. You see the difference, right? One is everything is happening within Hadoop. Second is something is happening outside Hadoop using the proprietary tools, such as first few tools, for example, Alteryx, Datameer, and so on and so forth, Talent. So these are some 2, 3 tools which allows you to play with the big data. So in this case, everything is happening inside the box. This is another big picture. So things to understand is the bottommost part is what we call it as HDFS, Hadoop Distributed File System. This is the system that contains all of your raw data of your data lake. On top of that, there is a resource management because somebody has to take the ownership of managing the resources within the Hadoop cluster. That component is called YARN, yet another resource negotiator. And then on top of that, you are saying MapReduce, Hive and Drill, Spark, Spark ML, Storm, Kafka. Kafka is not a part of Hadoop ecosystem, but we generally process Kafka, use the Kafka for streamlining data. Solar, Uzi, HBase, Zookeeper. You can see there is a guard, so you can figure it out what this component would be doing. This is coordinating everything from and to the external world as well as internal world. Now we will see one by one each of these components. So HDFS is the first. So HDFS stores different types of large data sets, structured, unstructured, semi-structured. Any form of data you give it, it will consume. HDFS creates a level of abstraction over the resources from where we can see the whole HDFS as a single unit. We told that the data is distributed, but when you see from any external application, you don't have to bother about where does the data sit. The data sit as node 1 or node 2 or node 3 and so forth, right? For them, when you query it, all the data, let's say you write a query, select employee name, comma, department name, from employee, comma, department, put a Johan, where employee is equal to Krishna. Now, for you, it doesn't matter employee is which node and department is in which node. Ideally, it will be split across all the nodes, or at least if not all the nodes, then at least if the replication factor is 3, then it will be present in at least 3 nodes. So that to avoid, we will see why it is like that. For now, assume it is a span across the multiple nodes, and then department also spans across multiple nodes. So when the query fires and it comes finally, your query fires, let's say from Hive table. Hive is a bad example, but let's say you do something in Pig and you interact with HDFS directly through MapReduce. So it gets transformed into mappers reducers, but ultimate aim I am trying to convey you is the data will be pulled from multiple nodes. It will be wrangled, join, and whatever operation you need to do, you do it, and then it gets retrieved to the end user. Stores data across various nodes and maintain the log file about the stored data. So it maintains a metadata file through which we can come to know that this table or this data is present on which node. It has got two core components, name node and data node. So name node, if you will see, the name node and the data node, if you will see, it's like a master slave architecture. You assume there is a project manager, there are John, James, Ellis, and there is another guy. All of these are teammates. The project manager job is something like he assigns the work to the different people in the team, and his ultimate job is to collate all the work from the different people and make it a deliverable, right? Is the same analogy happens over here as well. Name node, the main task of name node is it assigns the work to the data node, and then the data node gets the work done. Name node combines the result sets and so on and so forth, and then the final output is sent back. So it's the same thing is depicted in the different slides. So John A, James B, Bob. So it is different projects are allocated to it, and this is the metadata. So John is having piece of work project A, James is having B, Bob is having C and D, and so forth. Simple question. What happens if one of the nodes goes down? So let's say you have four data nodes and you have one data node goes down, then what will happen? The analogy of the scenario is if one of the project team member goes down or not well or doesn't come to the office, then the remaining work will be done by the three of the available resources till either I replace James with someone else or James himself comes back, right? So in the same way, this also happens if you will see in slave node or data node scenarios. So if it goes down, the data will get redistributed, or let's say first of all, whatever data this guy has, a copy will be definitely present in one of these three, because replication factor cannot be one. It has to be at least two, or three is the optimum. That's the recommended design. And then if you will see, these three people will do the work what John is doing, or what that node which went down is doing. So this is what the HDFS is. Now we will quickly take a look at yarn. So yet another resource negotiator performs all your processing activity by allocating resource and scheduling tasks. This is clear in itself. It has got two services, resource manager and node manager. Earlier it used to call as controller, but recent version they changed the name as resource manager and node manager. Resource manager manages resources and schedule application running on top of yarn. Node manager manages containers and monitor resource utilization in each container. Resource manager receives the processing request. So any request, external request that is going to come will come to this place. Once it receives the processing request, it passes the request to the corresponding node manager. And node manager is installed on every data node, responsible for execution of tasks on every single data node. That's what it means. So resource manager we have seen is the master daemon. That daemon means process. Okay. So it's a master process that manages all other daemons and accepts job submission. Allocate first container for the app master. Node manager is responsible for containers monitoring their resource uses, CPU, memory, etc., and report to the resource manager. Then app master is one per application. Application master coordinates and manage map reduce job, negotiate resources from resource manager. Allocate cluster resources, containers. The key thing is the three part. App master is one thing, because app master, what does it do substantially? So first of all, you have in yarn one app master per application, coordinates, and so map reduce jobs, it coordinates and manages the map reduce jobs and negotiate resources from resource manager. So ultimately resource manager has to release the resource, saying that this much of space, this much of CPU, this much of memory is needed, and then it will go to the node manager, and then node manager is responsible for containers monitoring their resource uses, etc., and reports it to RM. So RM will check with node manager, is it available, not available, and then it will allocate the resource. What happens if the resource manager fails while executing application? So if a resource manager fails while executing an application, then it will when you restart it, it saves a checkpoint. Okay. So it will look into the checkpoint and it will restart the thing. So map reduce data processing using programming, there are two components, mapper and reducer. Mapper is the transformation, reducer is the aggregator. So that transformation means anything that you want to do with the data, you can do it in map part, and reducer is a aggregator, like in word count program, how many words that has been repeated in a given text file, right? So that sort of aggregation does by the reducer. Map function programs act like filtering, grouping, sorting, etc. Reduce, aggregate, and summarize the result produced by map function. This is just a high level diagram how the mapper and the reducer work. So what happens is map reduce program. The first thing is any data you will give, it will be reallocated or reassigned or something about it, and make it as a key value pair. Then the map runs on top of it, and then the third step is shuffle and sort. Ideally speaking, by architecture principle, ideally you should not shuffle and sort the data, but practically it's not true. You need to sort the data, you need to shuffle the data because data are lying in different nodes and you have to pull the data. So pull the data means you have to shuffle the data, right? Some IDs are coming here, some IDs are coming from second node, and then you have to sort that ID in the ascending or descending order, whatever it is. So practically it's not true, but ideally we should have something that will avoid the shuffle and sort because it's a very costly operation. And then the reducer will aggregate the data. Pig scripting. Pig scripting is one line of Pig Latin. Pig Latin is the language name. Pig runtime, you have something called Pig runtime called grunt shell. And you can write Pig Latin code. One line of Pig Latin code is approximately 100 lines of MapReduce job. See why all these things came into picture. Initially, there were only two things, HDFS as a file system and MapReduce as your programming thing. All these subsystem gets generated because MapReduce is so cumbersome. Just to write, give me top 10 employee of this company in this year, let's say. Very simple. You can write it in SQL, probably 4 lines or 5 lines maximum. But if you have to write it in MapReduce, you might have to write 2 pages of code. And that's where all the child systems took a birth. Pig is one of them. So data flow, data manipulation, Pig can do very easily. It loads the data, perform various functions like grouping, filtering, joining, sorting, and finally dumps the data either on the screen if you are using grunt shell or it stores the data in HDFS. Features of Apache Pig. Here are the features, basically ease of programming. As you can see, you don't have to write, 100 lines of code. You can write 4 lines of code and your job is done. So a lot of inbuilt operators are there, flexible, extensible, and optimization. So it does the self-optimization as well. Because ultimately this also gets converted into MapReduce job. Whatever you do in Pig will ultimately gets converted into MapReduce job. But for user, you don't have to write that big MapReduce program. Hive and drill. So Hive is nothing but the SQL, people call it, it's a brother of SQL, a data warehousing component which analyzes data sets in distributed environment using SQL-like interface. Two basic components, command line or JDBC ODBC driver. I would like to tell you that Hive is one method that is used to expose data from big data system to the external world. Hive, you can create tables and you can populate that tables. So let's say you have an aggregated table, Let me take an example. Let's say you have got sales by country and you have got sales by state in file in HDFS. So you can write a program to calculate the data at country level and dump the data in a table in Hive and expose that table onto the external world. External world through JDBC or DBC only. Your application can consume data from Hive, whether it's an app, whether it's a program, anything for that matter. Supports user-defined functions as well. Data warehousing software utility used for data analysis, built for SQL users, manages query of structured data, because ultimately it has to convert it into table, then the data needs to have it in a structured format. Simplifies and abstract load on Hadoop, no need to learn Java and Hadoop API. These are some of the use cases that I talked about. Data mining, very large scale of data set also you can expose through Hive. Modeling, and that's how people actually use it. Nobody can query directly on HDFS file, right? It has to come through some interface. Hive becomes that interface through which you can query the data in the HDFS. So these are some of the features, you can say. SQL type query, scalable, extensible, ad hoc querying, fast, and OLAP based design. If somebody asks me which system is getting used in big data percentage wise, then Hive would be one of them. Hive would be on top. Spark, probably, yeah, Hive and Spark goes parallelly. Why Spark? You have got Hive, you have got Pig, you have got HDFS, you have got MapReduce. Then why you need a Spark? The first line is actually one of the use case. It's not the only use case. So Spark has got 5 components: Spark Core, Spark mlib, Spark SQL, Spark Core, and there are two more. So Spark came into picture because of two reasons. Number one is the parallel processing of the distributed data set. Number one. Number two is the map reduce part is very cumbersome. Spark, you can write the same code what you write in map reduce in 5 lines versus 100 lines. Third, it does the data wrangling part very well. And fourth, it's super fast compared to map reduce because it uses in-memory computation. Spark is written in Scala. So if you want, you can do the Spark programming using Scala, Python, and R also. But Scala is the most favorite because Spark itself is written in Scala. As you can see that it's 100 times faster than Hadoop for large scale data processing in memory and 10 times faster than Hadoop on disk. So Spark comes packaged with high level libraries. These are all libraries actually. You need to know how to use this library and how to use that into your code, right? R SQL, Python, Scala, Java, and so on and so forth. One of the greatest use case is Spark streaming. So what happens is many of you would have heard about a term called Kafka. So Kafka is nothing but a message broker. Broker means it receives the message and broadcasts himself that I am having the message. Now it's up to the destination system to consume that message. So Kafka can just broadcast. It cannot do anything beyond it. Spark can take up the message from Kafka and then process it as per whatever logic you specify. So that's where Kafka and Spark combination is very deadly for streaming data set. mlib for machine learning, GraphX for graph computation. In Spark SQL, you can write SQL-like query using Spark Spark session and Spark context. There are two objects in Spark. Lazy evaluation. This is a good thing. So lazy evaluation, what happens is, let's say in any program you divide x equals 10. The moment you define x equals 10, it gets evaluated then and there. Next statement, if you will write y is greater than x, if y is 20, y is greater than x, it will tell you there itself it's a true or false. Lazy evaluation means unless and until there is an action being called from Spark, this statement will not get executed. So even though if you define x equal 10, it will not get executed there. It will get executed when you say action equals call x, HBase. So HBase is a NoSQL database and first of its own kind, part of Apache suite, an open source non-relational distributed database or a NoSQL database, supports all types of data, and that is why it is capable of handling anything and everything. It is modeled after Google's Big Table. It gives us a fault-tolerant way of storing sparse data. There is a small comparison, HDFS versus HBase. These are just at a high level difference. There are a lot of difference inbuilt, and which makes Apache HBase as unique. They are not competitor, by the way. All it is trying to show is what you do in HDFS, how easy it is to do it in HBase. Uzi. So Uzi is a job scheduler in Hadoop ecosystem. So from automation perspective, if you will think, then you need a scheduler, right? Uzi workflow and Uzi coordinator. So Uzi workflow is a sequential set of actions to be executed, and Uzi coordinator is Uzi jobs which are triggered when the data is made available to it, or event triggered based upon the time. So for your understanding, you just say that it is a kind of a scheduler which provides the automation. So you can program something, package something, and then you can schedule it using Uzi. Flume ingest unstructured and semi-structured data into HDFS. It helps in collecting, aggregating, and moving large amount of data sets. Helps us to ingest online streaming data from various sources. It's a data streaming specifically built for HDFS, HBase, Hive, Kafka, Elasticsearch, and so on. There is something called source, channel, and sink agent. There is something called agent, and each agent has three parts: source, channel, and sink. Source is where data is coming from and can have channel selector or interceptors. Channel is how the data is transformed, file, memory, etc. And sink is where the data is going, can be an organized into a file, or a sink can connect to one channel, next channel, and so on and so forth. This is what the flume is. These are some of the advantages you can see: scalable, reliable, fault tolerant, centralized data storage, data ingestion, large data set, real time. All you have to remember is scalable, reliable, and real time data streaming out of so many boxes. Scoop. So Scoop, main task of Scoop is in and out of data from RDBMS to Hadoop and Hadoop to RDBMS. Flume only ingests unstructured data or semi-structured data into HDFS. See, there should be a method to ingest the data into HDFS, right? Some canal which can feed the water inside the cave, right? So that kind of scenario, if you will see, Flume is one of the input to HDFS. Scoop is another, but Scoop is from relational databases like Oracle. Zookeeper. So an open source server which enables highly reliable distributed coordination. For this purpose, Apache Zookeeper coordinates with various Hadoop services in a distributed environment. It performs synchronization, configuration, maintenance, grouping, and naming. Many of the high availability system needs zookeeper from Hadoop perspective, because what happens is, even though if you will see in map reduce part, it talks to zookeeper for availability of all the nodes or which nodes are available, because what happens is it coordinates between all the components of the Hadoop ecosystem. Apache Ambari. So Ambari is again a UI for provisioning, managing, and monitoring the cluster. Gives us a step-by-step process for installing. You can actually, using Apache Ambari, you can configure the entire cluster itself. It's so powerful. So basically, it's an admin screen at the end of the day. These are some of the other, like for example, Flink, Storm, Zeppelin, Tage. If you run Hive on Yarn versus Hive on Tage, Hive on Tage would be a lot more faster. Storm. So Storm is another framework for processing continuous streams of data on a cluster. Can run on top of Yarn like Spark. Work on individual agents and not micro batches. If you need sub-second latency, Storm is for you. Kafka plus Storm is also a very popular combination. Zeppelin is basically Zeppelin is a notebook interactively run scripts or code against your data. Share the notebook for collaboration. Can run Spark code interactively. So which is a very good thing. Otherwise, what you have to do is you have to open a Spark shell. You have to run the Spark code, and then if you want to test in that scenario, and then you have to again put it back into your code. So like many of you would have heard about Jupyter Notebook, which is used for Python. Similar thing, Zeppelin is used for Spark, and SQL queries directly against the Spark SQL. And it can also give you the visualization in charts and graphs. Mesos is the last one. Mesos is also a resource negotiator, but it is much more broader than Yarn. Solves a more generic problem than Yarn. Not just for big data stuff, it can allocate resources for web servers, small scripts, etc. as well. It came out of Twitter. Manage resources against your. Spark and Storm may both run on Mesos. Yarn may be integrated with Mesos using MyRed. Okay. Thanks everyone for joining.